Well, hello again, everybody. It's wonderful to see you tonight. Here we are in Peyton Hall, home of the Astrophysical Sciences Department of Princeton University, where we have a splendid evening arranged for our last formal get-together, at least regular meeting of the season. We will, of course, continue to meet during the summer at our observatory at Washington Crossing Park, and you can learn all about that on our website. Access to the telescopes and astro video astronomy in real time. But for tonight, we have a few things in store. Of course, the main event will be coming up in a moment, and I'll bring Victor, our program chair, up here to introduce tonight's speaker. Further down the agenda, after the break, we'll come back, and as you probably noticed from some of the emails heading your way, we have an election of the officers of the AAAP tonight. So this is the board. And the board election will proceed immediately after the break. We do have a slate, I've been told, so this is good. After that, we'll go into astro activities going on in the club, and quite a bit of celestial happenings over the last couple of months since we last got together. And we'll be talking about what's been going on from a member's eyes perspective. And please feel free to share some of your experiences. We're going to talk about eclipse. We're going to talk about how members ventured far and wide up and down the line of the moon's shadow across the continent, and we want to hear those stories. We'll also talk about another unusual event that happened just this last weekend at Aurora in New Jersey. Are you kidding? But really, we have that to talk about. And then we'll get into some mainstays of the club, what's happening out at the observatory, and some events going on in outreach. And then if there's time and you are so inclined, to have a few things to say about our ongoing AAAP observing challenges. And I've had a couple that have been pending. And I don't know about you guys, but I've been seeking some answers to those observing challenges. And I've got a couple of things to share with you tonight. So if we have time at the end, we'll get into that. Enough said about the preamble here. I think what we're really here for tonight is to hear our main speaker. So I'm going to ask Victor to please come up. Victor Davis, our program chair.
Okay, well, it's my pleasure to introduce tonight's guest speaker, Dr. Temim, and her topic is peering into supernova. Hold this. Okay.
You keep going.
With the James Webb Space Telescope. Okay. In terms of a synopsis of her talk, supernova explosions are among the most energetic events in the universe, and they play a key role in shaping the energy balance, structure, and chemical content of galaxies. Despite their great importance in astrophysics, key questions remain about what type of stars produce supernovae and how they explode. In its first year of observations, the James Webb Space Telescope has provided an unprecedented view of supernova explosions, allowing us to peer into the deepest layers of ejected material, illuminating early dust formation and revealing remarkable, never-before-seen details in the structure of young supernova remnants. Dr. Temim will review some of these recent JWST observations and what they tell us about supernova explosions. A few words about our guest speaker tonight. Dr. Temim, am I pronouncing that correctly, or even Temim, who immigrated to this country with her parents from Bosnia, we learned earlier this evening, and moved to Minnesota. She earned her PhD from the University of Minnesota in 2009. She was subsequently a predoctoral fellow, then a postdoctoral researcher at the Center for Astrophysics in Smithsonian. She was a research scientist and postdoctoral fellow at NASA Goddard. She recently worked on JWST's mid-infrared instrument called MIRI at the Space Telescope Science Institute. Her research focuses on understanding how supernova explosions of massive stars affect their environment and enrich the interstellar medium. She's particularly interested in the evolution of supernovae remnants and pulsar winds, the connection between stellar progenitors and explosions and their observed remnants, dust production, and processing by supernovae and dust evolution in galaxies. And I want to thank you very much for agreeing to speak to us this evening. Dr. Temin.
All right, so this is a brief outline. So first I will give some background on this topic, tell you why supernovae are important and what we can learn from these remains of supernova explosions or supernova remnants that we observe in the Milky Way galaxy and nearby galaxies. And then I will tell you about 3 different remnants that were observed with JWST in the first year of observation, so in cycle 1, and they are okay, so just to give some background here, I am showing a diagram that shows the evolutionary paths of low-mass sun-like stars on the left, and on the right, the evolutionary paths of massive stars that are about 8 times or more massive than our sun. And throughout most of their lives, stars are fusing lighter elements into energy. The material will be shed without an explosion, and it will produce what we call a planetary nebula. What remains in the center is the core made up of carbon and oxygen that we call a white dwarf. And then these white dwarfs, when they are in binaries and interact with a binary companion, they can produce what we call type 1a supernova explosions. And these explosions are used as standard candles in cosmology, but I'm not concentrating on these types of explosions today. What I will talk about today are supernova explosions that are produced by the massive stars. So if you look on the right side of this diagram, you will see the evolutionary path for the massive stars. And in these stars, the densities and the temperatures are hot enough for fusion to continue until an iron core remains in the star. And because fusing iron takes a lot of energy, does not produce additional energy, at that point, energy production will stop and there will be a gravitational collapse of the core, producing a supernova explosion. And these explosions are what we call core collapse supernova explosions. And what remains in the center of these explosions is usually a neutron star, a pulsar, or a black hole. And supernova explosions, as you probably know, are among the most energetic events in the universe. To give you an idea, one supernova explosion produces about 10 to the 51 ergs of energy. And this is actually approximately the energy that our sun will produce in its entire lifetime of 10 billion years, but it's given out on a very short time frame. So because of this incredible energy that's released in a supernova explosion, these events have a great influence on the energy balance, the structure, and the chemical content of galaxies, like this beautiful image, JWST image that you see here of the galaxy NGC 1566. And supernova explosions also enrich galaxies with heavy elements and dust grains that condense out of that ejected material. And from that material, the new generations of stars form, as well as planetary systems. And I always love to show this periodic table that basically summarizes the origin of the elements that are color-coded by the mechanism by which they are produced. And what you can see here on the right there is the makeup of the human body and color-coded in the same way. And if you just to draw your attention to the orange parts of the periodic table, all of those elements are produced in these core collapse supernova explosions. So collapse of these very massive stars. So basically 3/4 of our body was produced in these explosions. But despite how important these explosions are for virtually all areas of astronomy, there are still some fundamental questions that we don't understand about these explosions. So for example, we still don't have a complete understanding of what types of stars produce, or what types of systems produce the supernova explosions that we observe in our own galaxy as well as in other galaxies. And also, we don't yet have a complete understanding of how they explode. And the variety of the core collapse supernova types that we observe are broadly divided into these different subtypes, the type 2 and type 1 supernova explosions. And these types are based on the appearance of the optical spectrum of the supernova when it explodes. More specifically, the type 1 and type 2 categories are based on either the presence or the absence of hydrogen in the optical spectra. So if you look at the type 2 explosion on the top, you will see a spectrum with hydrogen lines. That's why it's called a type 2. And then when we get to the spectra that don't show hydrogen but only show helium, we call these type 1 explosions. And so now we understand that those types are directly related to the structure of the star before it explodes. So you might have seen a figure like this before showing this onion skin type structure of a massive star. So basically in the core of the star, the densities are the highest and temperatures are highest. And then as we move out to the outside, you get a reduction in the temperature and the density. So we have these different shells of lighter and lighter elements fusing into other elements as you move out from the core to the outside. So in the core, we have iron, ash, and then we have silicon, magnesium, neon, oxygen, carbon, and on the outside are the helium and then hydrogen shell in the outermost layers. And when we observe an explosion, the explosions that show hydrogen are those that from stars that had their hydrogen shell intact when the star exploded. But if a star somehow loses that outer layer of hydrogen and then explodes, then we might get a type 1 explosion that doesn't show any hydrogen in the optical spectrum. So the question is, how did the stars actually lose those outer envelopes? So again, I'm showing these. This is a more simplified picture now of the type 2 and the type 1b explosions that show helium but not hydrogen, and then there's the type 1c that don't show hydrogen or helium. So how did the stars lose the mass? Well, initially, we used to think that this is always a function of the stellar mass. So as the mass of the star increases, you are more likely to lose that outer envelope through strong stellar winds, because the higher mass stars produce a lot of radiation. So there's radiation pressure driving the wind, and that outer envelope gets lost. So, this would be, in this scenario, we would have, as the stellar mass increases, you are more likely to go from type 2, type 1b to 1c explosion. But we now understand that a large fraction of these stars, of massive stars, are actually in binary systems. So if you have two binary stars that orbit each other interacting, a binary companion can actually strip that outer envelope even from a star that isn't so massive. So now that picture becomes more complicated. In some cases, it might be the strong stellar winds. And when we see a type 1c explosion, it's a massive star. But in other cases, it might be a lower mass star that is in a binary companion and had the envelope stripped. So now, one of the questions that we're trying to answer, we're trying to disentangle what type of stars produce the explosions that we observe, because that picture is now much more complicated. It's not just a function of mass. Okay, and one way that we probe these questions is through observations of supernova explosions in other galaxies. We expect a supernova to occur about twice per century in a galaxy like the Milky Way, but the closest supernova that we have observed in our lifetime was in the Magellanic Cloud, and this is supernova 1987A that I will talk about later. But then we observe thousands of supernovae in other galaxies, and this plot here is showing all the different supernova types that you can see in the top right there, plotted on the map of the sky. So there are many of these that we observe, and and probing these questions through observations of these extragalactic supernovae is a very active and exciting area of research, but it's not what I will concentrate on today. My research focuses on the remains of supernova explosions in the Milky Way galaxy and surrounding galaxies. And these explosions the remains are much older, but they range in age from anywhere from 150 years, or in the case of 87A, just decades, to tens of thousands of years old. And what makes these explosions very powerful for probing these supernova remnants, very powerful for probing the questions, is that unlike those extragalactic supernovae where we look at spectroscopy, but they're only a point of light, they're so far away, they're not spatially resolved. In the supernova, when we have an explosion that occurred in our own galaxy or in a nearby galaxy, once that material expands, we can actually spatially resolve it. So in these supernova remnants, we can actually map the distribution of the material that was ejected in the explosion, but the additional aspect that we can probe is that mass loss that happened prior to the supernova explosion. Because the supernova shock is driven into that material that was shed by the star prior to explosion, we can also study what the properties of that material. So these remnants give us a view of what is happening in the explosion, but also what happened prior to the explosion. In this map of the galactic plane and at radio wavelengths, you can see all these little circles in the galactic plane. Those are all the different supernova remnants that we see in the Milky Way. There are actually over 350, I think now close to 400 supernova remnants that have been discovered in the Milky Way. And as I mentioned, they range in age anywhere from a couple hundred years old to tens of thousands of years old. And these supernova remnants bear the imprint of the supernova explosion and allow us to study the material that was ejected. And what I will concentrate on today, or what I concentrate on in my research, is the remnants that tend to be younger and that are dominated by the ejected material. So for example, I'll show this in a little bit, but as the remnant ages, the shock of the explosion starts sweeping up more and more of the surrounding material. And at some point, when the remnants get very old, the emission that you're seeing is almost completely dominated by the material that was not associated with the explosion, but it was swept up in the surroundings. But if we study some of these remnants that are very young, they tend to be ejecta dominated. That means the emission is mostly coming from the material ejected in the explosion and the mass that belonged to the star but was shed prior to the explosion. This is just, these are just some of the remnants. These are mostly X-ray images, but I'm just showing you this to show you the variety of the types of morphologies that we observe in these remnants. And each one has its own interesting story. Each one has its own progenitor system. And today I will only talk about 3 of them, but something that I will not have time to talk about today are these remnants that host pulsar winds. I'll mention what there is in a moment. Those are remnants that I am most interested in. There's the Crab pulsar wind nebula shown in blue. I guess you guys can point out it on the screen here. And I'll explain what that is in a moment. But first, I want to tell you about what we are actually observing when we look at a supernova remnant. And I'm doing that with the help of this diagram that just shows the basic structure of a supernova remnant. So when the star explodes, we have the forward shock that expands very rapidly into the surroundings. And that is shown by this yellow circle. That's the forward shock. And that shock will initially sweep into that material, that outer envelope that might have been shed by the progenitor star. And then the regions in the inside that are colored in light yellow are the freely expanding supernova ejecta. Those ejecta cool very quickly, and in supernova remnants, we usually can only detect that emission in the infrared. But once enough material has been swept up by the forward shock, a reverse shock will form, sort of like a reflected shock, and begin propagating towards the inside. And then it reheats those freely expanding ejecta in yellow to million-degree temperatures, and then they emit in X-rays. And so what I'm showing on the right here is this beautiful X-ray image of the supernova remnant Cas-A. And the blue outline that you see are the high energy particles, which represent basically accelerated synchrotron emission from accelerated particles at the forward shock. So that the blue outline is the forward shock, and that colorful shell that you see on the inside are the supernova ejecta that have been reheated by the reverse shock and are now emitting in X-rays. So you're now seeing all of those different colors represent different elements. The key is there in the corner. So silicon in red, sulfur in yellow, calcium in green, iron in magenta. But the material that is still in yellow that hasn't been yet reached by the reverse shock, we are not going to see in X-rays. And that's what we need the infrared for, and that's what I'll talk about in a moment. So I want to mention that some of these remnants that have pulsars in them, that have pulsars that remain after the explosion, produce pulsar wind nebulae. So a pulsar is a rapidly spinning neutron star with a very high magnetic field. And as the spin of the pulsar slows down, that loss of the rotational energy powers a wind of very fast energetic particles like electrons. And those electrons are then, and positrons are accelerated in the pulsar's magnetic field. And when they're accelerated, they emit radiation that we call synchrotron radiation. And it's emitted across the electromagnetic spectrum. So and this is what we call a pulsar wind nebula. This is the most famous one, I would say. It's the pulsar wind, it's the Crab Nebula, as seen in X-rays. And you can see this sort of torus of emission, and the emission from that pulsar wind nebula mimics the structure of the magnetic field. And so if we have a supernova remnant, the pulsar wind nebula surrounds the pulsar, and that pulsar can be thought of as this very high pressure, low density bubble that expands inside the ejecta. And one example of such a system is the Crab, and I'll come back to that in a few slides. Okay, so the questions that we are trying to answer is, what types of supernova explosions produce the remnants that we observe locally? So we want to, when we observe these remnants, we sort of want to do stellar archaeology to determine what kind of explosion produced it. Can we say something about the progenitor star? How massive was it? Was there a binary system? Those kinds of questions. And then also what remnants can tell us about the explosion properties and that pre-supernova mass loss that is directly related to the types of explosions that we observe in other galaxies. And that now brings me to the observations with JWST. As I mentioned, there have been 3 remnants that were observed in cycle 1. And I will talk about each one. But I first want to give you just a bit of a brief reminder. I am sure that most of you do not need this reminder, but JWST launched on December 25th of 2021. It's about 1.5 million kilometers from Earth, orbiting at L2. It has now been taking observations for, wow, it's been 2+ years. And it has given us observations in infrared wavelengths that have an unprecedented quality. JWST mirrors are shown here compared to the Hubble mirrors. They're about 6.5, effectively 6.5 meters in diameter. This provides a resolution at infrared wavelengths of about 0.1 arc seconds, which is extremely good. The wavelength range that is covered is between 0.6 and 28 microns, so the near to mid infrared wavelength range. This figure shows the footprints of the JWST instruments on the sky, of the detectors on the sky. And there are 4 instruments, and each instrument has multiple capabilities. And what I want to draw your attention to are the imaging detectors of NIRCam, which observes in the near infrared, and MIRI, the mid-infrared instruments, which is shown on the top right side. The footprints of those instruments are shown. So for example, the MIRI detector is about 74 arc seconds by 113 arc seconds. And I'm showing this because, as you see, with the remnants that we observe, this is actually compared to the remnants themselves. This is a relatively small field of view. So when we want to map these objects, we need to point many times and create and take images of separate tiles and then put them together into mosaics to produce images of these supernova remnants. I also want to mention one other capability that both there 2 instruments have, NIRSpec in the near IR and MIRI, and these are the integral field units that provide imaging spectroscopy of very small regions. So let me see if I can even find them to point here. So the this integral field unit word that we use for spectroscopy, this is the field of view here, this tiny little region. And for NIRSpec, it's right here. So just to give you an idea that they're very, very small footprints on the sky. But basically, what an integral field unit does is there's an image slicer. So basically, if there's an image, it's sliced into different parts, and then light from each slice of the image is then sent through a slit or a prism and dispersed into a spectrum. So then what results from this kind of instrument is basically a data cube that gives us the spatial information like this, but then each spatial pixel of the object gives us also spectral information. So like for each pixel, we can actually see a spectrum that gives us all the lines of the different elements so that we can look at compositions and how they vary in a spatial way. Okay, so now I will get to the, I'm really building it up here to some actual images. First, this image of the remnant Cassiopeia A was taken with Spitzer. So this is the best resolution that we had in the infrared at 24 microns prior to JWST. And I will blink to the JWST image at a similar wavelength. There it is. That is the difference. Similar wavelength. So as you can see immediately, the difference is quite drastic. What we immediately see is that a lot of these fuzzy regions in the forward shock, so in the bright shell, are resolved into these tiny clumps of material. We can already see that the supernova, it's almost like the material like shattered like glass. It's in these really tiny clumps. And we also detect emission. So there's hints of emission on the inside here that you can see here. It's very fuzzy. You can see something there. But then when we resolve it, we are seeing these sort of incredible web-like structures that I will talk a little bit more about in a moment. But and now going back, I'll click back to the Chandra image to remind you that in Cas A, as I mentioned before, this colorful shell is material that has been reverse shocked. So it has 1,000,000-degree temperatures. That outer blue region is the synchrotron emission that is produced by particles accelerated at the forward shock. But one of the goals that we had with JWST is to search for that emission from material that is on the inside that has not yet been processed by the reverse shock. So sort of we see a fraction of the material here, but we don't see anything colder than what emits in the X-rays. And we want to see what's on the inside, the material that's unprocessed. And that's what we're searching for. And now I will blink to the composite image where all of the JWST filters that we use were put together to make an image. I'm sure you've seen this image before, but here it is. And I will point out some features that we see in the mid-infrared and how they differ compared to X-rays. So again, we see this shell of reverse shock material. This is the bright main shell. On the outside now, where we saw those emission from energetic particles in the X-rays, what you're seeing in this orange and red color on the outside and sort of the outskirts of the remnants is that material that was shed by the star prior to the explosion and is now emitting in the infrared. It's dominated by the emission from dust particles. And you can see that that material has an incredible, we can resolve this incredible structure. But the part of these observations that were most surprising as soon as we opened the first data set is this emission that you see on the inside. And this was got to be called the green monster. And I don't know, that is somehow stuck. It is green because, not because anything physical, but because it happened to be colored green when the image was put together. That particular filter where that structure is emphasized was colored green. So I just wanted to point that out. But basically, what is incredibly interesting about this structure is that when you zoom in, I don't know if you can see it in this image, we see these very circular structures like holes or like bubbles that it is unlike anything that we've seen before in a supernova remnant. And because one of our goals was to look for that interior emission from the material that hasn't been shocked, we thought when we first put together this image, that maybe this is that emission that we've been looking for. So for example, one possible explanation, this is just us brainstorming initially for these little bubbles, is if you can imagine, let's say you had some little clumps of radioactive material that was giving off emission and producing little bubbles. So, but we can't know, even though it appears to be on the inside, it could also be something in projection. So one of the first things we wanted to do with this data set is to try to understand what is this structure, what is its origin. So, as I mentioned, it could be in the interior, but it could also be in front of Cas A or behind it, and it could represent some kind of interaction of the forward shock with that material that was shed by the star, and it could just appear to be coming from the inside. And the first clue came from JWST spectroscopy. So we had a spectrum using one of those integral field units, so a tiny region, but here it is. We put the field of view is right on top of one of these little bubbles. And when we looked at the spectra, we could see that circular structure outlined in some emission lines. But what we found was a little bit surprising. So we found that it's in some filters is dominated by warm dust, so it's dusty. But the thing that was surprising is that the lines that we saw had very low velocities, almost close to rest. So that means that if it was supernova material that was ejected in the explosion, we would expect velocities to be much higher than that. So this was the first clue. The second clue, or the crucial clue, came from correlating the Chandra X-ray emission of Cas A with the JWST observations in the infrared. So this is that X-ray image now colored somewhat differently, but just in blue. And what I will overlay now is JWST data as well as Spitzer and Hubble. So it's lots going on in this image. But let me show you. I'll blink back and forth. This was an image release for the 25th anniversary of the Chandra X-ray Observatory. Just as a side note, I put this image here of the website savechandra.org. As many of you may know, the president's proposed budget for 2025 includes pretty much the cancellation of Chandra, which we are all very sad and disappointed about. And It may not be too late. So if any of you are interested, what some of us could do, please go take a look at that website. But basically, now when we look at Chandra and JWST in comparison, maybe you can see already that some of those structures in that green monster actually correlate with some of the X-ray structures that are seen. I don't know if you can see my mouse, that are seen here. So our approach now was then to find the regions that correlate, that are part of that structure, and look at the spectra in X-rays to see if we can get some clues about what that emission is, where it's coming from. And that is what I'm showing on this side. On this slide. This is a paper recently published just about a month ago. And what you're seeing there is, so the green outline is the outline of where the green monster is. And what you're seeing on the right are spectra extracted from that region compared to spectra in X-rays extracted from regions that we know do not come from the supernova, but are in the outskirts and come from that material that was shed by the explosion. So, so in this case, when we compare them, we see that they're very similar. So the clue from the X-ray emission, that emission from the green monster is actually circumstellar material. It's material that was shed by the star prior to the explosion, and now the supernova is interacting with that material. And it actually happens to be in front of Cas-A. So it's mostly blue shifted emission, but it's unfortunately not that material that we've been looking for on the inside. But when we take a spectrum from the center of Cas-A, where we kind of a region that looks blank, and we look at the shifts, we take the shifts of the line. So this is the spatial region of that integral field unit, and these are. And the way that you can think of this is we have a line detected in the spectrum, in this case, an oxygen line, and we looked at it, and there are multiple oxygen lines shifted to different wavelengths. And then we converted those shifts to velocities. So if you take a pencil beam through the remnant, you can see this incredible structure in velocity, which basically translates to a 3D structure. So there is emission there. It's just not easy to see. And we basically then, so this is a burnt-in image in one filter, 25 microns, that shows you the shell of reverse shocked ejecta, that green monster region on the inside. It's all very saturated. But then we use the combination of these imaging filters to subtract out the emission from the reverse shocked ejecta and the green monster. And this is what we get. So this is the emission in the interior of the supernova that has not been processed by the reverse shock yet. So this is the most detailed view that we've ever seen of the structure of the ejected material in a supernova. It's most detailed than we've ever had before. And now something like this can be directly compared to theoretical simulations of supernova explosions that can predict some of these structures. So this was pretty incredible. And see if I have anything, right? So it's this web-like network of this unshocked oxygen ejecta. So I'll move on. Could I just ask for how much time I have left? Start a bit. Okay, perfect. Okay, so that was a little glimpse of what we found for Cas-A, but now I want to move on to the Crab Nebula, one of my favorite objects. This is the Hubble Space Telescope image of the Crab. The Crab Nebula resulted from a supernova that went off in 1054 AD, and back then it was observed by Japanese, Chinese, Arab, and European astronomers. So we know the precise date of the explosion. And this supernova remnant has actually been studied for hundreds of years at this point. And it's also the first object that was recognized to have resulted from a supernova. And it has been used as a benchmark for understanding neutron stars and pulsars. So it's pretty much one of the most studied objects in astronomy. But despite that, there are still some questions that we don't understand about the crab, and some of those are basic. Like, for example, we still don't know what type of explosion produced it. And that is one of the questions that we are trying to answer with JWST. This is now what the crab looks like with the Spitzer Space Telescope. The view is a little bit different than the optical. I want to explain a little bit what you're seeing, and I think it'll be much more clear in a moment. But the Crab Nebula has a very energetic pulsar and a pulsar wind nebula. So this pulsar wind nebula that I explained on one of the previous slides, what those are, you can again think of it as a high pressure, low density bubble, and it has rapidly expanded into the supernova material and first swept it up in a shell, but then instabilities formed called Rayleigh-Taylor instabilities, where the mass of that material kind of started sinking towards the center, and it formed these filaments. And I will show the 3D structure in a moment that will make it more evident. But the pulsar wind nebula was so energetic that it probably swept up pretty much everything that was ejected in the explosion. And so this is what the crab looks like in the infrared, or what we had up until the best resolved observations that we had up until recently. Here you can see the pulsar wind emission a little bit better. It's colored in the blue light. And now you see those same filaments in the infrared. In this case, the filaments are in an infrared light. They're dominated by the small dust particles that condensed in the ejected material, and as well as in this image in particular, oxygen emitting in red. And what I want to show you here is this incredible movie that is actually not an animation, but was constructed based on over 300,000 individual spectra of the material in the Crab Nebula. So the spectra were taken, and then different lines identified, and their shifts were converted to velocities. And then assuming uniform expansion, you can convert those velocities to a 3D structure. So that's what I will show you here. And then you can really appreciate what we're looking at when we look at the Crab Nebula. So the hazy blue color is the pulsar wind nebula on the inside, and it has expanded into the ejected material, and all that material is kind of forming a cage around the pulsar wind nebula. So if you rotate it in 3D, this is sort of what you're looking at when you look at the 2D images. It's one. So it's so all that material is sort of like a cage around this bubble. So when we add up all of the material that's emitting that we can observe, it adds up to about 7 solar masses of material, and that material has a relatively low velocity that then would be expected in a supernova explosion. So the material is moving at an average velocity of 1,200 kilometers per second. And if you take the 7 solar masses, the velocity, and convert that to a total kinetic energy, the total kinetic energy in the crab is less than what we would consider a typical supernova energy. It's actually less than 10% of a typical energy. So now there's a consensus that the Crab Nebula was a low energy supernova explosion, and that its progenitor star had a mass between 8 and 10 solar masses or so. So if you add up the 7 solar masses in the ejecta, maybe 1.5 in the pulsar, it's the whole thing. And for many years, the Crab Nebula, because of this low explosion energy, as well as some other properties, it has been thought to be the best example of a certain kind of supernova explosion that is theorized, but not yet entirely confirmed, and that's an electron capture supernova. So it is theorized that stars that are not quite massive enough to keep fusing elements in the core all the way up to iron can actually produce this different type of supernova explosion that is called an electron capture supernova. And in this explosion, the core is made up of oxygen, neon, and magnesium. And that core exceeds a critical mass, at which point the electrons are captured by neon and magnesium, the pressure in the core is reduced, and this leads to a collapse. And The Crab Nebula was thought to be the best example because of the very low explosion energies. And an additional observation that pointed towards electron capture supernova are these observations from the late 80s, early 90s that indicated that the Crab Nebula has a high abundance of nickel relative to iron. And that, and such a high abundance is predicted in some of these electron capture explosions because these explosions are expected to have a very neutron-rich material. So you would expect stable nickel to be much more abundant. But there's some inconsistencies with that. One in particular is that the pulsar in the Crab is moving relatively fast at a velocity of 160 kilometers per second. And the pulsars can get a kick if there was an asymmetry in the explosion. But these electron capture theoretical models for electron capture supernovae tend to be very symmetric and only produce about 10 kilometers per second or so. So there's an inconsistency. The pulsar velocity points more towards an iron core collapse supernova. So what we wanted to do with JWST is to go back and remeasure those nickel and iron abundances in a much more accurate way, which we can now do with JWST. And the reason it's much more accurate, first, we're looking at infrared wavelengths, so we don't have some of the previous observations were in the optical, so we don't have to worry about extinction and things like that, the extinction from dust. But also, we have much better spatial resolution. To give you an idea, before JWST, with Spitzer spectroscopy, this is the largest, smallest region for which you could get a single spectrum. It's about 4 arc seconds. But with JWST, with those IFUs, or integral field units, that we can now get an individual spectrum for those smaller squares that I'm showing. So you can basically get spectroscopy in a spatially resolved way. And because these filaments, these eject in the Crab, is these very complex ionization structures, the ratios of the lines vary. You want to compare the smallest regions possible to each other so that you're not mixing different parts of the ejecta, and you want to compare apples to apples. So this is what we set out to do. We mapped the Crab with JWST. These are those individual tiles that we had to put together. And I'm going to do the same thing that I did before. Here's the Crab with Spitzer, and I'm going to show you what we get when we use the JWST. Okay, that's the difference in the spatial resolution. And I want to show you this incredible image produced by Joe De Pasquale. I know he was also a speaker. This is now using all of the JWST filters to produce the image of the Crab. I'll tell you what I'll tell a little bit about what you're looking at. That hazy white color are filters that only include that emission from the pulsar wind. So here you're seeing those emission from the particles that are accelerated in the magnetic field. The filaments that you're seeing in this image are made up of, well, they have many more elements in their composition, but the filters that we use cover iron and sulfur. And the sort of greenish color that you can see in these inner regions comes from dust, so warm dust particles. And we concentrated, because remember that for spectroscopy, the field of view of that detector is tiny, tiny, tiny. So we would love to get the entire Crab, but that's just not possible or feasible, or it never will be, at least not currently. So we picked two very interesting regions where we thought we could find emission from nickel and iron, and we wanted to compare these ratios. I'm zooming in on that region here. This is, again, a much bigger zoom in than the actual IFU footprint. That's how big the field of view is. So we're really just getting one clump of emission, but I just want to show you with spectroscopy, this is now extracted from that spectral cube. We took a line of nickel and made an image just integrated over that line. So you're basically looking at the distribution of the nickel line at 10 microns So you can see how well we can spatially resolve it. So I actually won't share. So the result, we calculated nickel to iron ratios and compared them to models for the iron core collapse versus electron capture. We have a paper that's going to be published in the next, hopefully, couple of weeks with an associated press release. So I will not share it today, unfortunately, but it's coming very soon. Please keep an eye out on what the results from this are. I do want to show you something else that we were able to do. Bear with me here. I'll just want to explain how we did it. For the Crab Nebula, each of these filters that we use to do the imaging contain many different emission components. And before, we've never been able to fully separate out the emission from the warm dust particles that condensed in the ejecta from emission from like elements like lines of oxygen or sulfur. And we were able to do that for the first time with JWST and show what the distribution of the dust that condensed in the ejecta looks like at high resolution. And we were able to do that just because of this very convenient way two imaging filters overlap. And this is what I'm showing here. So this is a spectrum extracted from one of those knots in the Crab Nebula. And I have colored the different emission components that contribute to these spectrums. So for example, the blue emission is the emission from the pulsar wind, what's colored in blue. The pink colored regions is the emission from the dust grains, the warm dust grains. And then I've colored the lines, emission lines from elements in green, but then I colored one particular line of sulfur, which is the brightest line in the spectrum, in orange. And when we look at and what's overplotted in these very, I hope you can see these very light shaded regions, are the filters for the images. So for example, this is the filter in the gray color at 18 microns. And when you take an image, all of the emission that's under that curve in that filter is included in the image. And it turns out when you look at the filaments, really the thing that dominates is that sulfur emission because that line is so bright. This is on a log plot. But you'll notice that those two filters overlap right where that sulfur 3 line is. So that means that both of the imaging filters contain that line. And if we subtract them from each other, we can actually get rid of that line and then see what the rest of the distribution looks like. And this is what we did. So we used this small region where we have a spectrum as a test. So again, I'm showing these are the two filters, 18 microns and 21 microns. In a single filter, this is the contribution from the different emission components. And then if we subtract them with some weighting factor, we can actually completely get rid of the orange emission. What we're left with is the residual that is dominated by dust and has a contribution from the pulsar wind nebula. But because we also have images that sample the pulsar wind nebula by itself, we can subtract that out too to be left with only the dust emission. So I'm going to show you what that looks like when we apply it to the whole image. Here's a filter, an imaging filter at 21 microns that contains the pulsar wind emissions, the synchrotron emission, the sulfur line, and the dust. Now I'm going to subtract the synchrotron. There it is. Now we're left with just the ejected material, but now that includes sulfur and dust. And now I'm going to subtract the sulfur. And what we're left with is the emission just from the warm dust grains that condensed in the ejecta. And I want to sort of compare that map to this image. This is now the Hubble image in oxygen in green, the pulsar wind in blue, and here's how the dust overlaps. And you can see that the dust is in those inner filaments. And you can think of, or the way I think of this map is that the dust condensed in the material that is densest, where it's very dense. That's where the dust particles form. So really the dust is tracing where the densest material is, so where most of the mass is. So we have the very dense material on the inside with the density decreasing as you go out to the outer regions. And one thing that I want to compare that to is this these simulations, the hydrodynamical simulations that were done for a system like the Crab, in which a very energetic pulsar wind nebula is sweeping up supernova ejecta. So So I'll explain it very quickly, but basically a typical supernova ejecta profile, when you look at density, looks like this. It's flat, and then it has this steep drop off. And in these hydrodynamical simulations of such a system, when the pulsar wind is expanding into the flat part of the profile, the radius of the pulsar wind and where most of the mass is, the half mass radius, are very close together. But when the pulsar wind reaches the steep part of the profile, its radius just starts accelerating and kind of punches through the ejecta. And now, in this scenario, if it's in this part of the profile, you have most of the mass is sort of left at these lower radii, and the radius of the pulsar wind is much higher, much greater than where the ejecta is. And that's kind of what we see in these observations. We see most of the material is, if it is kind of sunk more towards the center and is not out the outskirts of the pulsar wind nebula. And this sort of tells us, confirms that the pulsar wind has swept up most of the material because it's already in that steep part of the profile, just based on this morphology. And could I please have a time check? Just to know how much I have, about 5 or? Okay, great. So the last object I want to mention is supernova 1987A. This is, of course, the youngest remnant. Now we can consider a remnant. We see the expanding ejecta. This is a supernova that we observed in the Large Magellanic Cloud in 1987. What you're seeing here is the Hubble image. The expanding supernova ejecta are on the inside here, and what's on the outside, this ring of emission, is actually what I mentioned before, that material that gets shed by the star prior to explosion. And supernova 1987A is small on the sky, and it's actually perfect for an observation with that integral field unit, because actually this entire image fits into one field of view for the integral field unit. So that means like we can take an image and get a spectrum from each pixel. This is an image of 87A with JWST. The ejected material is colored in blue, and from that cube of the spectroscopic cube on this image, we were able to construct the 3D structure of that ejected material, again, using the velocity of the iron 1 line at 1.4 microns. The ring here is that circumstellar ring that's on the previous page, and the 3D view of that ejected material is what was reconstructed from the JWST observations. Another, I'll say this, actually I'll skip this next part just for the sake of time. But another thing I wanted to share is that one of the most exciting discoveries from the 87A data set was the evidence for the compact object in the supernova, which we have not detected before. And this also came from these spectroscopic cubes. So this is, again, the image of 87A. Here are the ejecta on the inside. And what you're seeing here in these series of images is the velocity. So we have taken imaging slices of that cube centered on the argon 2 line. So you're seeing different velocities of the argon 2 line, and we're stepping through velocity. So these are blue shifted on the very top, and then as you move across and to the bottom, you're getting to blue shifted emission. And what I want to draw your attention to is this image where it's circled in the center. This point of emission pops up in the center in the light of argon 2. And I'll show that on the next slide. Here's a spectrum extracted from that region on the right. There's a bright line of argon 2, but it was also detected in some other lines like sulfur. And this emission coincides with the very center of the ring. And we took that line emission and tried to understand where it comes from. And there are two models, two scenarios that can reproduce that emission. One scenario is if there is a hot neutron star that is now cooling and heating the ejected material around it, giving rise to that argon and sulfur emission from the ejecta. The other scenario is if there's a pulsar wind nebula. If there's a pulsar and a pulsar wind nebula that is photoionizing supernova ejecta, giving that point-like emission of argon. With the current data, we cannot distinguish, but both of these scenarios require the presence of a compact object in 87A. So this sort of we're indirectly detecting the compact object. And we do have a new data set that we will, new observations taken with JWST that will be combined with this in hopes of trying to disentangle which of these scenarios is more consistent with the observations. But this was very exciting. So I will end there. I will leave this, I can leave the summary up or just say, just to summarize this talk, supernova explosions of massive stars influence all aspects of astronomy. But as I mentioned, there are still questions we don't understand. Studies of these very young supernova remnants that are dominated by the supernova ejecta gives us lots of insights about the explosion and what the distribution of the ejected material is, so that we can then directly compare that to theoretical models for these supernova explosions. And these new observations with JWST, and especially when we combine them with other wavelengths, are really giving us an unprecedented view of supernova explosions. I showed a tiny part, but I think these observations just taken in the first year can keep us busy for many years to come. But I also want to say we observed some of the most exciting ones, but there's so many remnants out there that we hope to observe. I only showed some of my favorites. I'm saying some of my favorites, there are many more, but we do hope for more observations in the future and to keep and to continue to connect the properties of these supernova remnants to the explosions that produce supernovae in other galaxies as well. Thank you very much. I'm happy to take questions.
It was a picture with the star and with the inner layers composed of different materials. So I wonder, how do you know what this star is built of, especially like the inner layers? Or it is only when it explodes you can tell what it was composed of?
Right. So especially for the inner layers, a lot of that composition and the profiles come from theoretical calculations for what we take. There are stars of different density profiles and structures that are then exploded and nucleosynthesis is calculated. So then there are, from theoretical calculations, profiles of what types of elements you should see in each layer in these supernova explosions. But then we are also able to, in a lot of cases, observe this nebular phase of supernovae. So when the gas expands enough that we can actually probe into the inner layers and look at spectroscopy in these extragalactic sources to compare that composition to what the predictions are. And we can do the same in supernova remnants. In supernova remnants, it gets tricky because when things get older and the reverse shock interacts, things get mixed and also with the surrounding material. But it's a combination of observations and theoretical predictions.
When you were showing a picture of the supernova 1987A, the inner ring was sort of blobbed up. It was a series of blobs.
It's clumpy. Yeah.
Why?
So it's so the ring, we think the ring was produced by the mass loss a star experienced prior to the explosion. Perhaps there are some models that suggest that 87A was produced by a merger of two stars, or that ring could have been produced as because of the way that the progenitor star rotated, like the mass that it lost ended up in this sort of disc-like or ring-like emission. But it's really that as that mass is lost, there's clumping of it's just that material ends up clumpy as it's expanding into the surroundings and encounters other surrounding ISM material. And there's maybe clumps of dust in some regions that are slightly denser. Dust begins to condense, so you get these. We probably don't resolve the physical scale of these clumps. They're probably very small, but because they're dense, they end up being much brighter when they're encountered by the shock.
Is the information that you're gaining about the structure of these supernova remnants helping you to predict what the progenitor star will be so that we can point to one and say, aha, that's a candidate for a supernova explosion in a billion years or something?
I think it's more, I don't think we're quite there yet for that kind of prediction. I think it's more, so this is how I would describe it. We're trying to use these supernova remnants to understand. So for example, if we can look at a supernova remnant, like for example, 87A, we see what the circumstellar material looks like. If we can determine the mass of the star that exploded, we want to understand how, for a particular type of explosion in a particular mass star, what type of environment, surrounding environment, and ejecta structure will that type of explosion and system produce? And then we can apply that to all these thousands of other extragalactic supernovae that we observe, for which we also get information, but not in a spatially resolved way. So it's more like to understand the population of the stars that produce supernovae and what the distribution in terms of numbers of those systems are. I don't think we could probably say some general things about what type of star is expected to explode, but to really say anything in terms of like how soon or anything like that, I don't think that we're anywhere close to that.
Thank you for a very good session, very informative. I have a rather basic question, so
it's okay.
No judgment. We say dust, right? For other things, you are able to do spectroscopy, but for the dust, why is it called dust, and what's the composition? Do we know?
Right. So these are small solid particles that form when the densities are very high. The different atoms condense into these solid particles. The dust, it can have many different compositions, but what's most typical in supernova remnants, for example, that are from lower mass stars like the Crab, models show that when we model the ejecta and the elements that are present and how they cool and what the densities are, the explosions like that tend to form mostly carbon dust. So it's small solid particles of carbon. As we move up in mass, sorry. Oh, it's tiny. It's basically like yeah. Sorry? Like smoke, exactly, like smoke. So you can imagine, yeah, like cigarette smoke or fire smoke. That's how small the particles are. Exactly, thank you. And then as we move up in mass, because the composition of the star changes as the star increases in mass, then different types of compositions become more likely. So if a star is more massive, then we tend to form more dust that has oxygen and silicon in it. So the solid particles, for example, like magnesium silicates and things like that. And I didn't have time to talk about this, but depending on the dust particle in the laboratory, emission from these dust particles can be measured, and we can construct optical properties and show what the spectrum should look like. Each type of dust ring has its spectral signature, sort of. So we can use these spectra that we take in the infrared to also determine what type of dust might have formed. That's also a very interesting talk. I can actually suggest speakers for that because it's also something very exciting, because we're actually observing dust formation in real time with James Webb in these extragalactic supernovae.
Thank you.
Yeah.
Hi, Dr. Temim. I have a question, if you can hear me. I was just curious if there's any simulation done on stars with respect to their outer layers, if they happen to be unlucky in the path of some sort of jet stream coming from a black hole, and how that might affect the star's eventual explosion.
Right. So I think the question is, if I heard everything correctly, if there's some sort of jets from a black hole, how that might affect the exposure of the structure of the supernova remnant.
Right.
There is a particular remnant that one of the, I believe in the Small Magellanic Cloud, that had this sort of interesting kind of double lobe morphology and was suggested to perhaps harbor a black hole. I don't know what the latest on that is, but there are certainly remnants that do have these interesting structures where it looks like they have, you know, they're dominated by these like jet-like emission. It's sometimes very difficult to disentangle, or one of the things that we do with supernova remnants, we try to disentangle how much of that structure that we observe is intrinsic to the explosion itself and how much it's actually shaped by what the surrounding material looks like. So if you imagine, for example, that in 87A that has a ring of circumstellar material that is very dense, and if you have an explosion that happens from the center, because it's contained along that equatorial plane, then the ejecta might actually end up with a double structure because of that containment. So it's actually a very interesting question. Something that we work on is try to disentangle what is intrinsic to the explosion itself. Did the explosion have jets, or is the structure caused by just like what the supernova is expanding into? Yes.
Thank you.
When you see like the supernova, what is producing light?
So in the remnants or in the supernovae, so in the supernova remnants, we have, so if I go back to this picture that I showed here, the structure of a supernova remnant. Oops, sorry, it's way too far back. So in this picture of the structure of a typical supernova remnant, what we have, there are different emission components, and there are many different things going on. So we have, on the outer shockwave, we have a shock that is driven into the surrounding material, and that material is heated and photoionized. So then we have line emission from the different elements. Then we have these solid particles of dust that are heated as they collide with atoms, and as they're heated by the shock, they're heated to a certain temperature, and they just kind of, like any body that is heated to a certain temperature, they emit radiation. But in that case, radiation will not look like just a single line as you get from an atom, like a transition of an electron in an atom, but it will actually be distributed across the electromagnetic spectrum. Then another emission mechanism is what I mentioned from these pulsar winds. And so whenever a particle is accelerated in a magnetic field or by the shock, it can emit radiation. So we have pulsar winds, which is radiation from these accelerated particles, but then we also have this emission in blue that surrounds this remnant that is also accelerated particles. So there are all these different components. There's lines from the atoms that emit radiation. There's the small solid particles that emit radiation, and that signature looks differently. There's the synchrotron emission from the pulsar wind and accelerated particles. That also has a different signature. So we can actually, when we get a spectrum, we can oftentimes figure out what emission components are present and where the emission is coming from. And depending on the object that you're looking at, there can be different contributions. In some cases, we only see pulsar wind nebula with no obvious supernova remnant. In some cases, it's only the ejected material. In other cases, it's mostly dusty if we look in the infrared. So it depends both on the emission mechanism, but also what wavelength of light we're looking at. I hope that wasn't too long of an answer.
So I'm curious to understand where the energy comes from to make the reverse shock. Because it was started off going out and now it's coming back in. What caused, was it gravity or was it energy from the other?
It's basically the buildup of the material. So the reverse shock, it's kind of like having a reflect. If you drive a shock and then the density of enough material is swept up that the density is high enough that you get basically a shock reflects back because it hits to like a density that's high enough. It's crashing into something, exactly.
What is the duration?
Duration of the explosion. So You mean the supernova explosion itself? Oh, right. So it's very short. It's on the order of seconds, basically, very short. And depending on the type of simulation, it might have, like that duration might vary somewhat. There's actually Adam Burrows in the department, works on simulations of core collapse supernova explosions and has shown us some of these simulations and the timescales on which they occur. But very fast.
You say it lasts for seconds. Did you say seconds?
This is just what the initial explosion. I'm not talking about the evolution of the remnant. It's just the instant that when the actual supernova explosion occurs. Basically, when the supernova, the gravitational binding energy is converted into the kinetic energy.
You've got a question about duration is a great way to end this talk.
Okay.
So thank you again.
Thank you.